So I want to, if possible, try to leave you a little time. I don't know if that's going to be possible or not. I want to look at just a couple more, but I don't want to waste your time either. So you guys kind of give me a little feedback after we go through a few of these, and if you think that's enough, you can maybe work and ask questions for the last part. So quick reminder of our 4 steps. I think we're probably all pretty familiar with those by now. Here are some examples of problems that show up on the second of the 2 assignments. I'd say of the 2 related rates assignments, the second one, I don't know. I guess I initially intended it to be a little bit more, have the little tougher problems, but I don't know if it really does, honestly. This one's a little bit tough. I'm not going to go through this one with you. I want you to have the joy of doing this one all on your own, but I will briefly discuss it. I just want you to see that this problem, the one with the inverted conical water tank, is exactly the same problem that we did yesterday with the sand pile. Same thing, right? Same thing. It gives you the dimensions of the tank, right? The tank is, in this case, for this particular problem, has a height of 8 feet and the radius of the tank is 4 feet, right? Water is drained through a hole in the vertex at a rate of 3 cubic feet per second. Let V be the volume of water in the tank and let H be the depth of the tank. And they kind of lead you through this, which is nice. They want you to write an equation that relates V and H. So in other words, we're writing volume as a function of height only, right? Just kind of think about how that's going to work. We've got our formula, and I'll write that down. We know the formula for the volume of a right circular cone. You guys remember what that was? There you go. 1/3 pi r squared h, right? That's got r's and h's in it, but we want to be able to write volume as a function of h only. So what's our strategy if we want to eliminate r? What are we going to do? My goal is to get volume as a function of h only. I don't want r's in there. So what do I have to do to get rid of the r? Say it again. Plug what in? The number value of r? I can't do that, right? Because if I plug in a number value of r, when I differentiate, that's going to look like a constant, and it's not a constant, right? As the water level decreases, the radius of that little cone of water that's sitting inside the tank is decreasing, isn't it? So I can't do that. I can't plug in I can't plug in any values of variables until after I differentiate. What do you think, Becca? There you go. Good. I want to find another equation that relates r and h and isolate the r and substitute, don't I? Right? And that's going to come just from similar triangles here, isn't it? Right? Now these are constants. The dimensions of the tank are constants, but the variables r and h are meant to represent the height of the cone of water and the radius of the cone of water. Both of those are changing, aren't they? Right? And you got it. We could just use similar triangles, and we could say something like r over h. That's an r. Look like an r, does it? Equals what? 4 over 8, which is 1/2, right? So we could use that to write r equals some function of h and then substitute, right? Get the idea? Okay, good. And that'll give us volume as a function of h, and then it's no big deal. Then the calculus, we've got a single independent variable, one input variable, the output variable v, I just implicitly differentiate with respect to t and plug and chug. Now, when we're doing our snapshot values in this one more thing I'll draw your attention to, and then that's all I'm going to say about this one. They give us v dot, don't they? Because look at the units. What's the value of v dot here? It's not 3. It's -3. How come? Okay, because the volume is decreasing, right? So the rate of change of volume must be negative. So V dot would be -3. Okay? Make sense? Okay. That sets you up for that one. Okay. This is another one. Maybe it's worth just taking a quick look at this. This is on the second assignment. Okay. 6-foot tall woman walks at 9 feet per second toward a street light that is 24 feet above the ground. What is the rate of change of the length of her shadow when she is 13 feet from the street light? Okay. What's the first thing we would definitely do here? Draw a picture. Yeah, for sure. We're going to draw a picture on this one. Okay, let's do that. Here, I'm going to do that. Okay, yeah, so we could draw a picture, right? We've got, there's our street light. Can I write 24 for that? Yeah, I don't need a variable, do I? How come? It's not changing, right? So we'll write a number in for that one, 24. What about her height? 6 feet, and that's a number, right? That's a constant. Okay, and I guess maybe we need like a light ray there, don't we? So this is her shadow, agreed? Everybody see what we're doing? Okay. So what are my variables? Okay. Between her and the light, and what do they call that? It looks like they're telling you, let L be the length of the woman's shadow and let X be the woman's distance from the street light. Okay, so then this is X, correct? And this is L, right? Make sense? Okay. And we're just trying to, what do we know, I guess, on this one? And then this is all I'm going to do. What's the stuff that's given to us? Okay, so what is that? Everybody agree? If she walks towards the street light at 9 feet per second, we have to think about that in terms of a rate. That's the rate of change of her position with respect to time, right? So this must be X dot. So what's the value? Is it 9? How come negative? Because it's decreasing, right? Her distance from the street light is decreasing, so the rate is negative. That's a real common mistake people make. And then what are we looking for? L dot. Okay. How could I probably do that one? Give you a big hint.
Don't we have to include X and L inside that?
Could be, yeah. But how could I set that up? I just need some equation that relates X and L, right? That's my parent equation. So what's that going to be? Similar triangles. You see that? There's a temptation sometimes for people to want to do things like use Pythagorean theorem. Everybody see why that's not going to work? Because we don't know anything about the hypotenuses, right? Okay. So we just want to use similar triangles. So we'd say something like the big triangle, and let's put the variables on top just to make the algebra a little bit easier. So the big base divided by the big height equals what? So we're looking at the big triangle is this whole big right triangle, right? Okay, good. It's going to be the small base over the small height because they're similar triangles. That's all I need, right? Now I'm good. Okay. From there, it's just some algebra and calculus. And then the last part, notice this part. They want you to find at what rate is the tip of her shadow moving? How am I going to do that one? That's different than L dot, isn't it? Right? L dot is just the length of her shadow that she's casting, but she's moving too. How would I do the second part? Any ideas?
The x plus L dot.
Yeah. Okay, so for part two, I might even think about a different quantity. Let's call this entire quantity, I don't know, let's call this thing uh, D for distance or something, right? Call it capital D. And then we've got, now we have for the second part, we have a relationship D just equals X plus L, right? Okay, I should be able to do some calculus with that and find D dot then, right? Okay. Good? Okay. This one came up on the first assignment. I think it looks like a lot of people asked about this one. Do anybody want to see this? Okay. So what's a little bit people that finished this one, was this one tough? Once you saw the hang of it, it was pretty quick, wasn't it? Right? Yeah, and the part that's a little tricky about this, and the important part with all these, really, the calculus isn't very hard usually, right? It's just setting it up that's the tricky part. So if we're going to build our rectangle, our variable rectangle, what are we going to do here? Let's call maybe the base X and the height Y, something like that. There's our rectangle. When we add our snapshot values, what is this part right here telling us? What is that? It says all sides begin increasing in length at a rate of 4 centimeters per second. So what's that telling us? In our picture, what are our sides? How do we represent our sides? Those X and Y, right? So then what are they telling us here? Yeah, good. X dot and Y dot, they're the same, aren't they? All the sides are increasing at the same rate. So this part is telling us X dot and Y dot are both positive 4. Okay, what we're missing though is X and Y, right? Okay, so if we look at this picture though, they tell us something else. They tell us, or they ask us, at what rate is the area of the rectangle increasing after 18 seconds? So they're kind of telling us what the time is in our video when we're choosing our snapshot, right? Our frame in the video. It's at 18 seconds. Well, if these are the values we're starting at, how much have each of the sides increased after 18 seconds? How much? How'd you get it? Yeah, right? 4 centimeters per second times 18 seconds gives us the amount that the sides have grown, right? Right, and that's, what is that? 16, what? 32? They've each grown by 32 centimeters. So then what is, at that snapshot value, what's the value of X? If we're going to say X is the one, let's call this X, and let's call that Y. Oh, times, what did I do? Times, 18, whoops, okay. So that's going to change it then. That's going to be 72. So then what's the big dimension going to be? If it starts at 7?
Oh, 79.
79, yeah. So here's our snapshot. That's 79 centimeters, and the small dimension would be 75. So really, this is just giving us one more piece of the puzzle. It's telling us initially x equals 79 and y equals 75. And there's all of our snapshot values, right? And that's pretty easy. Okay, then our nice thing about this is our parent function's easy, right? It's just an area. Area equals xy. So let me ask you this. Were you tempted to want to try to eliminate a variable here? Like we definitely in this, I'm going to scoot back for just a second. In this one, we needed to eliminate a variable, right? We needed to eliminate r and write volume as a function of only one variable, okay? For one thing, we didn't really know, they didn't tell us anything specifically about the rate of change of the height. Now, we could have figured it out, right? We could have figured it out, but it would have made things more difficult. In this one, do I have a real strong motivation to eliminate a variable? Not really, right? I mean, if I did have some information, I would, but I really don't have any. I don't really have any information that allows me to easily eliminate a variable. And the calculus is pretty simple anyway. If I differentiate with respect to t, what do I get? A dot equals what? How am I going to differentiate the product x, y with respect to t? I use product rule, right? So that's going to give me x, y dot plus y x dot. And I have all that stuff, don't I? So it's easy. Okay? All right. Okay, this is a good one. I want to, and you might see something like this potentially on the test, something like this, okay? This, I just like this so much. So watch this one really carefully here. How do you think the rate of change of the volume of a spherical raindrop will evolve as it falls through a layer of uniformly dry air with constant temperature and humidity, okay, and evaporates? So we're gonna have to make a couple assumptions here, but just think about this. This is so cool that we can do this, that we can come up with this pretty easily. So what's gonna happen to that raindrop as it falls, a spherical raindrop falling through a layer of dry air? What's gonna happen to it as it falls through the dry air? Okay, it's gonna evaporate, isn't it? When it evaporates, what does it lose? Okay, but mass doesn't really help us here. We don't know anything about mass, but it loses volume, doesn't it? Right? Where does it lose its volume? I mean, where does this stuff evaporate from the raindrop? On the surface, right? That's the only place where it's in contact with the air. So that's where it's going to lose its water, right? Can you make any predictions about what might happen then? Like, well, say it again. The shape's going to stay the same. It's going to stay a sphere, right? But it's going to, I'll tell you what, never mind that last question. We'll just see what happens. Okay, so we want to show that the radius of the raindrop decreases at a constant rate with time. Okay, that's our goal. How could I do that? They don't really give me much here, do they? All they're really telling us, they're implying, is that it's losing its volume through the surface of the raindrop. Okay. Will you tell me, would it stay the same? If it's losing water through the surface when the raindrop is this big compared to when it's this big. Okay, what were you saying, Becca? As the surface area changes, what's going to change to the rate of evaporation? It's going to change too, isn't it, right? As the surface area decreases, there's less of an opportunity for water to evaporate because it only evaporates through the surface. How do we say that relationship mathematically? The rate of change of volume, right, which is just the rate of evaporation, is what? We said it has to be related to the surface area. What's the mathematical word we'd use for that? Say it again. Not inverse. What's the other thing? Proportional, right? Everybody get that? Right? So the rate of change of the volume, which is the rate of evaporation, is proportional to the surface area because they're gonna increase or decrease in tandem. Agreed? When the surface area is cut in half, then the rate of evaporation is cut in half. Okay, that's a big concept there. So what's that tell us then? We can write that this way. We could write that as V dot is proportional to surface area. That's our symbol for proportional to. Okay, that's a really interesting and valuable statement, but it doesn't equip us to do a lot of math because we can't really do algebra with a proportionality symbol. Right? So how do we turn that into an equation then?
Wait, what is the S represent?
Surface area.
The change in volume is proportional.
The rate of change of volume is proportional to surface area. Isn't that what we said? Right? The rate at which it's evaporating is proportional to the surface area of the raindrop. How do we write that as an equation? You guys remember how to do that? It goes clear back to probably algebra 1. Like if we have this statement, if we say that y is proportional to x, how did I write that as an equation? Well, I mean, maybe, but probably not. It's possible that could be correct. Think what that means. If y is proportional to x, if x doubles, what does y do? Doubles. If x triples, y triples. Okay, yeah, it's some constant times x, right? And we call it k, where k is the constant of proportionality, right? Does that make sense? And really what this looks like then, if I were to graph this thing, doesn't it just look like, it just looks like a line with a slope of k, right? That's what the graph looks like, okay? So then we're going to go up here and do the same thing, right? We could say that V dot is equal to Ks. And we could even do one more thing. We could say something like, is V dot going to be positive or negative here? It's going to be negative. So we could even do this if we want to. We could even say negative Ks, where K is a positive constant. Or we could just say K is a negative constant if we wanted. Okay. Does that make sense? Okay. So that's what has been implied by this thing. Okay. Now what can we do with that? We want to show that the radius of the raindrop decreases at a constant rate. Well, we didn't say anything about radius here. How could we involve radius in this somehow? That looks kind of like a related rates equation, doesn't it? I mean, I'm relating a rate of change to something. So what do you think? How did we come up with related rates equation? Yeah, we differentiated a parent equation, right? Okay, what would the parent equation be here maybe?
Oh, V equals R pi r squared.
Okay, that's surface area. That might be useful to know. So let's write that down, right? So surface area for a sphere is what? Not pi r squared though, it's remember. Didn't ring in a bell, huh? Okay. Surface area pi r squared. Okay. And then what's the volume of a sphere? 4/3, how about? 4/3 pi r cubed, right? Okay, make sense? Okay, so one thing we could do is we could make that substitution here. We know what S is equal to. So we could rewrite this as V dot equals negative K times 4 pi r squared. Okay. Well, now at least we got a radius in there. What else could we do? Okay. Yeah, we could differentiate the volume parent equation, couldn't we? Right? If we start with the volume equation, let's pick a different color for this. If we start with that parent equation, and I differentiate implicitly with respect to t, what am I going to get? V dot. Good. Because look, when I've got the 4/3 pi as a constant, the derivative of r cubed with respect to t is just 3r squared r dot, right? So when I multiply that 3 times the 4/3, look, I get a 4 pi r squared. Ideas? What do you mean plug it in? Yeah, look, I've got two expressions for v dot, right? So look at this. Then if I combine those, I'm going to get, on one side, I've got 4. If I plug in like to this v dot, I get 4 pi r squared r dot equals negative k times 4 pi r squared. What can I do? Yeah, I can divide each side through by 4 pi r squared, and look what I end up with. R dot equals negative k, where k is a positive constant. Okay, what are we trying to prove? Radius of the raindrop decreases at a constant rate. We did it, right? If r dot equals negative k, if r dot is a negative constant, that's what we just said. The rate of change of the radius is negative and constant, so the radius is decreasing at a constant rate. How about that? Okay, that's pretty cool, isn't it? We can do that without, we weren't given anything. We were just given a situation, and we applied a little calculus and physics, I guess. I mean, not really much physics, right? Okay, questions on that? Okay. You want to go through this one or not? It's on the, I'll tell you what, all I'll say about this one, what are the variables in this problem? We know that in general, the volume of a right circular cylinder is just pi r squared h. So I've got this piston, it's plunging down into the cylinder and decreasing the volume, and it gives us some information about how fast it's moving and stuff, right? What are the variables here? Height is a variable, and volume. Is the radius a variable? No, the radius is 2, isn't it? Right? So our parent equation here actually ends up becoming volume equals pi times 2 squared, 4 pi h, right? Pretty easy. The key to that one is you don't want to treat r like a variable. You don't need to. R is a constant. Okay? Then that becomes a pretty simple problem. We already did one kind of like this. Remember we did the one on the parabola. I'm going to not do that one. And I don't think we really need to do that one either. That's pretty similar to the increasing rectangle one. I think that's good. Why don't you guys just work?